Finding the derivative of a piecewise function, Part 3. In this part, we are going to go over the correct solutions from these calculus puzzles. So we had these two calculus puzzles, Part 1 and Part 2, where the procedure used was somewhere incorrect. And your objective was to find what was wrong with the solution. So in this first part, we had this piecewise function, and the questions were, is this function differentiable at x equals 2? And if so, what is the derivative at x equals 2? So what we did is we said polynomials are differentiable everywhere on negative infinity to infinity, and that is true. Polynomials are differentiable everywhere, so that was fine there. And then what we did is we said, well, this is a polynomial, 3x squared minus 1, so we just took the derivative using the power rule here, f prime of x equals 6x. And then since we wanted to find f prime of 2 there at x equals 2, we just plugged in x equals 2 and got the derivative of 12. So the problem with this is really just defined at this one point at x equals 2. Even though we're using a polynomial, it's really just defined at x equals 2 at that one point. So we could have just defined the function like this. Because if we were just to plug in x equals 2 here, we would have 2 squared, which would be 4. 4 times 3 is 12, minus 1 is 11. This would really be the same thing. We're just expressing that one value, the one function value at x equals 2 with a constant instead of using an expression in terms of x. So this would be the exact same function as this, just expressed a different way for that one point. So if we use that same logic as we did here, we could find the derivative of this, which would be 0. Then we have a contradiction here. That gives us a derivative of 12. So again, this was incorrect because this value at x equals 2, the function value at x equals 2 is really just a point. And you can't find a derivative at one specific point because it is a limit as you approach a point. So one definition of a derivative would be this. So remember, a derivative really is a limit. And if you think about what this is graphically, so if we look at a function like this, say this is our graph of f of x, and let's say this is some particular value of x, and this would be f of x. This is some value of x plus h, where h is positive, and this is some value f of x plus h. Let's find first of all, the slope of the secant line. A secant line is a line that passes through two different points on your function. So we're going to find the slope of the secant line first. So if you remember, slope is the same as rise over run, or change in y over change in x. So we're going to look at the change in y over change in x, or rise over run here. Or you may remember the slope m equals y2 minus y1 over x2 minus x1. And here our y2 minus y1 would really just be the f of x plus h minus the f of x. Or you could also think of that as, and when we think about it as rise over run, this is the same as our rise. And then our run here would be x plus h minus x, which this would just simplify to h. So this would be our run, or also you could think of the x2 minus x1. This is our x2, x plus h, minus our x1, which was our x. This coordinate minus this coordinate. And again, we have, this is the point then x, f of x, and this is our point x plus h, comma, f of x plus h. So again, slope being rise over run, the slope of the secant line would be the change in y over change in x, or we're going to have f of x plus h minus f of x all over h. And this would be the slope of this secant line. Now let's say we wanted to draw another secant line. So let's say here we would have, this would be x plus h. And here we're going to assume that h is actually negative. So h is less than 0. In other words, this is really like x minus something. So if h happens to be like -1, you're x plus -1, or you have x minus 1 here. So this would still be, in this case, this is a different f of x plus h. And we could still see that the change in y over change in x, or the rise over the run, you could think of this as f of x minus f of x plus h all over x minus x plus h, or x minus x plus h would be the same as x minus h, or just negative h. Now if we multiply numerator and denominator by negative 1, this would be the same as that, or you can think of this as negative f of x plus f of x plus h all over h, or we could change the order of the numerator so it is actually the same as that. These are both, this is just some other x plus h, f of x plus h somewhere on this graph of this function. Just kind of showing you that we can have an x plus h over here, and we want to think about now the slopes of these secant lines. Now the derivative actually is the limit of either of these expressions, which really is the same thing, the limit as h approaches 0 of these. So for example, if you cut h in half here, now your secant line that was that red line is now going to be, say, looking something like that. As h gets smaller and smaller, then you could think of this point here is going to get closer and closer to that point, and the limit as h approaches 0 actually becomes the slope of your tangent line. So we're actually going to have something like this for our tangent line. So again, as h approaches 0, your secant line approaches that tangent line. So let's just rewrite this again. This would be the same as f of x plus h minus f of x all over h. Both of these expressions represent the slopes of our secant lines. So the derivative is the limit as h approaches 0 of, sometimes we call this the difference quotient, or these are the slopes of your secant lines from either direction. Now if we wanted say the derivative from the right side, that would be with these positive values of h. We could say the limit as h approaches 0 from the right of this that would give us this tangent line as h is approaching 0 from the right. The slopes of those secant lines would approach the slope of that tangent line. On the left side, when h is negative, we would have, as h approaches 0 from the left side, remember these would be negative numbers then approaching 0. So that scenario would be these blue secant lines, and we would want, if h is approaching 0 from the left, these are negative values of h, but they're going to get smaller in size, closer to 0. So you may, as h gets closer to 0, you could think of this point as going to you could kind of think of it moving along this curve. So maybe if we take half as much for h, if this is our new x plus h, we'd have a point up here, and your secant line would be between those 2 points. But you can see again, as h gets smaller and smaller, these secant lines are going to approach, again, in this case, the same tangent line. So the limit from the left of our definition of derivative approaches the slope of that tangent line, and the derivative from the right also approaches the slope of that tangent line. So in order for a derivative to exist, we must have the derivative from the left and the derivative from the right, or that is the limit as h approaches 0 from the left and the limit as h approaches 0 from the right being equal to each other and equal to a finite number. If these are equal to each other and they're both finite numbers, we would have the limit itself existing, and therefore the derivative would exist, and we could find that derivative. If you're familiar with an absolute value function or a graph that looks something like this, we have this sharp point or sharp corner. If you use this same type of analysis that we did up here, look at finding the derivative from the left and the derivative from the right. In this case, you can see the derivative from the right is this positive slope. Let's say it's positive 1 slope. The derivative from the left side continues to be this negative slope. So this derivative actually right here does not exist. This is not differentiable at that particular, say this particular x value. Say x equals a, this would not be differentiable. Now we also need a function to be continuous to be considered differentiable. So let's take a look at why that would have to be true. So let's say we have a function like this and we try to find the derivative from the left and the right this time from this specific value of x. If we go over here to an x plus h and draw a secant line, we draw a secant line, we might have something like this. What happens as h gets closer and closer to 0 from the right side here? Our secant lines would look more like this. What's happening to that slope? As h approaches 0, these x plus h points are getting closer and closer to the x coordinate here, and your slopes of your secant lines would look something like this. This slope is actually going toward infinity. It's getting steeper and steeper and steeper. So if we look at the secant lines from the other side, we have maybe something like this. So as x approaches 0 from the left side, again, these would be like, so these would be negative values for h. And they'd be approaching, as h approaches 0 from the left side, this x plus h would be approaching your x. So on this side, the slopes of the secant lines actually would approach, say, a tangent line at that point, which would kind of go off. They would approach, say, a tangent line at that point that would look something like this. So here, say from the left, this limit actually would exist. It looks like it approaches some positive slope here. But from the right side, you can see these slopes actually are going to be approaching infinity. So what we have here is the limit as h approaches 0 from the right side of the secant lines are going toward infinity, whereas the limit from the left side of our secant lines would be approaching a specific finite number. Let's just call it m. So do you see here the two-sided limit of the definition of derivative would actually not exist. So the derivative right at this particular value of x would not exist if it is not continuous. So it's going to be important to know in general that whenever you have a discontinuous function at a specific point, the derivative cannot exist there. Let's go back to our problem here. So if we want to determine if this piecewise function is differentiable at x equals 2 or not, we need to check that this is continuous at x equals 2, as well as the derivative from the left and the derivative from the right are equal to each other, or that is like the limit as h approaches 0 from the left and the limit as h approaches 0 from the right, so that those two limits would equal each other. But we can just look at finding the derivatives from the left and the right, making sure that they are equal to each other. But again, we do need to check for both things. So why do we need to check for both? Well, can the derivative exist from both sides? This gets into part 2, the other problem, but we'll talk about that actually in the other one. But we do need to have the derivative from the left and the derivative from the right equal to each other, as well as being continuous. So let's check for continuity first. So how do we check for continuity at a point? Or how do we find if a function is continuous at a point? So one way to show that a function is continuous at a specific point is to use 3 conditions. We can say f is continuous at x equals a if the following 3 conditions are true. 1, f of a exists. 2, the limit as x approaches a of f of x exists. And 3, the limit equals the function value. So we could go back to this function, or we can go to our revised function where these would be equivalent. We just used 11 instead of the polynomial to express that one point. So do we have f of a existing? Well, yes. F of 2, if we look at this piecewise function, f of 2 will be equal to 11. So that checks. Secondly, does this limit exist? Well, for a piecewise function where you have an interval here where x is less than 2 and x is greater than 2, and we want to see if the limit exists at 2, we would need to check the limit from the left and the limit from the right. So let's do that. So the limit as x approaches 2 from the left of this function, as x approaches 2 from the left, that would be when x is less than 2, so we would pick this first expression. So as x approaches 2 from the left of this, since this is a polynomial, we can just go ahead and substitute this in from here. So plugging this in, we have 2 times 2 squared plus 3. Or we have 4 times 2, 8, plus 3 would be 11. And let's look at the limit as x approaches 2 from the right side of our function. So if x is approaching 2 from the right, we're going to use the third piece of this function, since that's when x is greater than 2. So we have the limit as x approaches 2 from the right of x cubed minus x squared plus 7. So again, this is a polynomial. We can just go ahead and substitute that in. And a polynomial separately would be continuous. That's why we can do this, actually, why we can just do a direct substitution. As x approaches 2 from the right, plugging that in, we have 2 cubed minus 2 squared plus 7. So we have 8 minus 4 plus 7. That is also equal to 11. So from this we know that the limit as x approaches 2 is equal to 11, since both the limit from the left and the limit from the right equals 11. So we have the limit as x approaches 2 of this function is equal to 11. We also have f of 2 equals 11. Therefore, this third condition is also true. You can see the limit as x approaches 2 of f of x is equal to 11, and f of 2 is also equal to 11. So this function is continuous at x equals 2. So this is our check for continuity. So we also want to check for differentiability. So to check for differentiability, we need to check the derivative from the left, which is going to be from x less than 2. And we need to check the derivative from the right, which is when x is greater than 2. So the derivative from the left, using the power rule, that's going to be 4x. So this is if x is less than 2. And from the right, using the power rule, we have 3x squared minus 2x. That's if x is greater than 2. So let's just say the derivative from the left So when I say derivative from the left, I'm really referring to the limit as h approaches 0 from the left of the slopes of the secant lines, or this part of the definition of the derivative, which we can use this to find that derivative from the left. So the derivative from the left will be, we should say, derivative from the left of x equals 2 will be 4 times 2, or 8. We also want to check the derivative from the right. Of x equals 2. So again, we can plug in x equals 2 here from the right. So when we say derivative from the right of x equals 2, we are really referring to this. The limit as h approaches 0 from the right of the secant lines, or again, the part of the definition of the derivative that is the limit as h approaches 0 from the right. So the derivative from the right, we can use this expression. we'd have 3 times 2 squared minus 2 times 2. So this is 2 squared or 4 times 3 would be 12 minus 4 or 8. So the derivative from the left and the derivative from the right are equal to each other. Or we could say the limit as x approaches 2 from the left of f prime of x is equal to the limit as x approaches 2 from the right of f prime of x. Or technically we should be using the limit as h approaches 0 from the left side of the definition of derivative, and the limit as h approaches 0 from the right side of the definition of derivative. So they are both going to equal 8. Our function here actually is differentiable. We do get the same value. We showed that it was continuous at x equals 2. We checked for continuity. It was continuous at x equals 2. We checked for differentiability, so you're checking from the derivative from the left and the derivative from the right of x equals 2. Those ended up both being equal to each other. So our derivative actually is going to be f prime of 2 would be equal to 8. If you have any questions, go ahead and let me know in the comments. Also, if this is helping, go ahead and give a like and a subscribe. So we'll go on to part 2. So now we'll look at the correct solution for part 2. In this one, again, we had a piecewise function, and we were determining, is the function differentiable at x equals 3? If so, what is the derivative at x equals 3? So what we did in the incorrect solution was, we said polynomials are always differentiable for all real numbers or on negative infinity to infinity. That is true. Then we took the derivative from the left and the derivative from the right. Now technically you should not include the or equal to there actually, because we don't know that the derivative exists right at 3 unless the two values are equal to each other, and also that it's continuous. Which, if you noticed in the last problem, we did say the derivative from the left for x less than 2, the derivative from the right was x greater than 2. So technically, the first mistake here was including this or equal to part. It should just be x less than 3 here and x greater than 3 here. That's the first mistake. And you do get the derivative from the left and the derivative from the right equal to each other. But the problem here is you do need to check for continuity. So why does a function need to be continuous and differentiable if we show that the derivative from the left and the right are equal to each other? Do you remember what we said over here? We said that the function must be continuous in order to have any chance of being differentiable. Because if you think about the limit from the right side of your slopes of secant lines, they're going to go toward infinity here, and the derivative from the left side you have approaching some particular constant. This limit would not exist. This limit would not exist, and therefore the derivative would not exist. Now, if you were just to look at the derivative from the right side and derivative from the left side, you could get the same slope on each side, say right here, as you approach, as h approaches 0 from the right side. Maybe if you were to have, say there was a point here, and you were finding the derivative from the right side, if this slope was equal to this slope, and you just found the derivative kind of separately as you approach from the left and from the right, you could get the same slope from either side. Again, actually the point doesn't really exist there, and you couldn't have both of these points being here because then it would not be a function. But again, this is a situation where you could show that the derivative is the same slope from either side, but if it's not continuous, it's still not going to be differentiable. As we showed here, the derivative would approach like infinity from one side and a constant from the other side. So the major mistake here was not showing that this function is also continuous. But also a minor mistake was also including the or equal to part here, because we really only can say this is the derivative from the left side, this would be the derivative from the right side. We can't say the derivative exists right at 3 until we say that until we verify two things, they would have to equal each other here, and also the function would be continuous. So again, the biggest thing here is that we need to show that this function is continuous. So let's do that. If you remember from part 1, we said we need these 3 conditions to verify if a function is continuous at some particular value of x. So we'll use those same 3 conditions again. We need to find if the function value exists, if the limit exists, and if the function value and the limit are equal to each other. So first of all, does f of 3 exist? Well, we do have if x is greater than or equal to 3, we have this. So f of 3 will be equal to 2 times 3 minus 3. And therefore we have 6 minus 3, or 3. So again, the second condition would be to show that the limit as x approaches a of f of x exists. So we need to show the limit as x approaches 3 of f of x exists. Well, for a piecewise function like this, where we have the function is defined one way for x less than 3 and one way for x greater than 3, or greater than or equal to 3, we want to find the limit from both sides. So let's find the limit as x approaches 3 from the left side. So if x is approaching 3 from the left side, that's going to be when x is less than 3, we would use this expression here. So then this is a polynomial. We can just go ahead and substitute the 3 in. So we have 9 times 2, or 18, minus 10 times 3, or 30, plus 9. So this will be, what, 18 minus 30 would be negative 12. Negative 12 plus 9, we're going to get negative 3. So let's look at what the limit as x approaches 3 from the right side would be. So if we're approaching 3 from the right side, we're going to use the expression where x is greater than 3. So that's going to be the 2x minus 3. So we'll have the limit as x approaches 3 from the right of 2x minus 3. So that will be 2 times 3 minus 3, which equals positive 3. Notice the limit from the left and the limit from the right are not equal to each other. This is not continuous at x equals 3. Limit as x approaches 3 from the left of f of x does not equal the limit as x approaches 3 from the right of f of x. So f is not continuous at x equals 3, and therefore it is not differentiable. So in answering this question, is the function differentiable at x equals 3? That would be no. And therefore there would not be a derivative value at x equals 3 either. Go ahead and post any questions or comments you may have. And if this is helping, go ahead and give a like and a subscribe. Thank you.